inverses, you have done inverses before. Okay? Okay, so you've done inverses back in math 20. You might recognize this number.
Yes.
Hopefully. No. Second time term, hopefully. Okay, so we are going to go through some of it, not all of it. No good. Right? Keep your, if you didn't keep your books from last year, start now. Because you're in IB, you're going to be writing an IB exam, okay, whether it's the SL or the HL. And it's not just on that last course. It's on everything in high school, right? So keep your binders. You have your, you have access to Schoology, but it's also nice to see your own work, right? So don't throw out your math binders. Or if you're taking any IB subject, because they're always similar in that respect. Okay, so it says relation. So a reminder, a relation between two variables can be described mathematically by a set of ordered pairs, a graph, an equation. Okay. Then this is back to math 10, right? This is review for math 10. What makes a relation a function? You're not in math 10. Well, in a relation, if each domain value is paired with only one range value. So I would say for every x value or domain value, there is only one y value or range value, right? Like if you know what x's and y's, then you use x's and y's. So for every domain, there's only one range. Then it's a function. If there's more than one, then it's not. So it says label each of the following as a function or not a function. So you look for every x. They're all different. So remember, with sets of ordered pairs, the way that you can determine if it's a function or not quickly is if there's a repeated x value with different y values, right? So there's no repeated x value. Here there is, and it has a different y value. So this is not a function. This is a function, okay? That is not the definition, though. So we asked you, what makes a relation a function? And you said, it is not a function if there's a repeated x value. There are, okay? For every domain value, this is the definition, right? Looking for repeated x values helps you determine if it's a function or not. And I think we probably asked you that on the test in that 10. Or we often do anyway. This one, it's a parabola, so hopefully you remember parabolas are a function. For every x, there's only one y. Vertical line test was the fast way. Again, it is not the definition of a function to say it passes the vertical line test. That is just a tool to help you. For every vertical line, it only passes once. There, for any vertical line, right? So that is a function. Here, except on the ends, it touches twice. So it's not a function. Okay. So this is review. That's review for math 10. Then 20, we talked about inverses. Now, in normal 20 1, we don't talk much about inverses except for maybe in sets of ordered pairs, but you don't get into the equations necessarily. We did, so this will be kind of review for you. And then obviously it's going to be on the diploma exam as well. So the inverse of a relation results when two variables are interchanged. So you start with y equals f of x, then the inverse is x equals f of y. Interchange x and y. So a set of ordered pairs. What do? Easy peasy. Switch them around. Okay. So in any case, this is the set of ordered pairs. What is the domain and range? 2, 3, 1. Actually, I'll put it in numerical order. So -5, 3, and 4. It doesn't, it's not wrong. We're not going to mark you wrong if you don't have it in numerical order. It's that's right? Now, the inverse, you interchange x and y. So 2, 3 becomes 3, 2. 3, 4, 4, 3. 1, -5, -5, 1. Now, if you look at the domain, 3, 4, -5, in numerical order, well, that was the original range. Range of the inverse, or, yeah, inverse 2, 3, 1, so 1, 2, 3. Makes sense. If you're interchanging x's with y's, then your original domain, x's, is now going to be the range of the inverse. So the domain of the original is the range of the inverse. The range, I'll just abbreviate, of the original is the domain of the inverse. Okay, now we're going to look at the specific linear relation. Equation is y equals 2x plus 4. The inverse, you interchange x and y. Then it says, reminds you, however, equations of relations and functions should be expressed in the form y equals if possible. So rearrange that so y is isolated. All for y. It doesn't say express in full y-intercept form or any particular form, so you can leave it in like this if you want. If it says slope y-intercept form, remember that would be splitting this up. So x over 2 or 1/2 x minus 4 over 2, which is 2. But it didn't specify what kind of form.
What's the other form that we use in point geometry?
General form. Point square. Okay, complete the table of values and graph the relation. So, here there's your original. X value is -3, so 2 times -3 is -6, plus 4 is -2. -4 plus 4 is 0. -1, or -2 plus 4 is 2. If these are going up by 1s, hopefully you remember, with a slope of 2, that means for every change of 1 in x, your rise is going to change by 2. Now, inverse doesn't have any values given to you. Okay, but what we just learned is if we take the inverse, we switch x and y. So -3, -2 would become -2, -3. And that makes sense here. So -2 minus 4 is -6, divided by 2 is -3. Okay, but you may have chosen just random values here, and that's fine. But given that we know this is the inverse, it's labeled, we just did that a minute ago, we can just interchange these, right? Then it says you need a table of values? Hopefully not for Math 10, given this form. This is the slope y-intercept form. So your y-intercept is 4, and your slope is 2. Up 2 to the right 1, or down 2 to the left 1. So I'm going to fill up my graph paper. When I'm drawing a line, yeah, you can get away with just drawing a couple of points, but how accurate are you? The more points you have when you get that straight edge or ruler and join them up, the better it's going to be. Because there's inaccuracies, right? Like if you're taking 2 points that are really close together, then maybe it's messing it up at the end. So I just keep plotting as many points as will fill in the graph paper. So that's my original. Now my inverse here, you can use the points if you want. You can think about my slope y-intercept form that I had on my previous screen. If you didn't have the table of values, right? In any case, you can see your slope, even if you just do a few of those, you can extend it to fill out paper, your grid paper. On the top. And take a look and compare it to that red line. Red line is not on yours, but this line here is the line y equals x. Y-intercept is 0, slope of 1. Okay? If you folded your graph on that line, these would overlap. Okay? So these would overlap and they're the same distance apart. So if you kind of look across here, that's diagonally 2, diagonally 2. Here it's going to be 2.5, 2.5. Same distance apart. So in inverse, that's why we put it in the transformation unit. It's actually a transformation. It's a reflection in the line of y equals x.
Would you do that before or after at the same time as you can show us how to do it?
Yeah, we're not actually, it's not part of the curriculum in 30-1 to do both, but you would do the reflection before translation. We don't do it with stretches.
Okay. Because that's kind of like,
but yeah, we'll do one together where there's 2 transformations, and I'll show you how you know that you do the inverse first. Okay, so line was already graphed. The equation of it was y equals x. What do you notice about the graph of the relation and its inverse relative? So they were reflections. Okay, there is an invariant point. Where is it located? On the line y equals x. The equation, the coordinates are -4, yeah. So the coordinates have to be the same. So in an inverse, when you're looking for invariant points, the coordinates of that invariant point are exactly the same number. If A or not, then it's not on the line y equals x. So it actually wasn't a variable. In this case, the relation is a function. Intercepts. Okay, well, we know the y-intercept, we don't even have to look at our graph, is 4. X-intercept is -2. You can check it out on the original. Okay, intercepts of the inverse. Green, the inverse, oops, the y-intercept was -2 and the x-intercept was 4. So notice how they interchange. Y-intercept becomes the x-intercept. X-intercept becomes the y-intercept. Same deal here. Okay, you can see a little title there saying now quadratics. Just kind of got shifted. Quadratic relation at the bottom of the page rather than the top. Now we're going to do the same with y equals x squared. Okay, so inverse of the relation. If we solve for y here, remember, when you take the root of both sides, we have to take the positive and negative root. Okay. If we don't, we're only going to get 1r. Because we're starting with a parabola. I can graph it, I'm graphing it without your table of values, right? You should be able to from math 20, 0, 0, 1, 1, and symmetrical, -1, 1. 2 over is 4 up, 2 squared is 4. Same on the other side. 3 over, 3 squared is 9. And same on the other side. Right? It's symmetrical without the axis of symmetry. So when I take the inverse of that, I need to have both arms. If I only said y equals root of x, I would only get 1 arm. Right? So if I interchange here, I'm not going to go through the table of values. You don't need to. So 0, 0 would stay. 1, 1 would stay. -1, 1 would become 1, -1. So now it's going to be what we call a horizontal parabola on its side. Hyperbola is kind of in that shape. It's got 2 parts, but it's got an x squared and a y squared in the equation. This point here, 2, 4 becomes 4, 2. -2, 4 becomes 4, -2. 3, 9 becomes 9, 3. -3, 9 becomes 9, -3. And you can fill in table values if you want, but you should be able to graph that. Take a look. If you folded your paper along that diagonal line, they would overlap, right? If you had sort of transparent that facing paper and folded it, then it would look exactly the same, okay? These points here do not move, right? They're on the line y equals x. Those are the invariant points. These points, same distance apart on either side. So that's your mirror line. You have a mirror there. This point straight across, same distance. These same distance, these same distance. Okay. That goes down the next page. Okay. What do you notice about the graph of the relation relative to the line? So they are reflections of each other. Remember, you can use in or about or over, I guess you could use. And the varying points, we pointed those out. The origin and 1, 1. They have to be on the line y equals x. So the coordinates have to be equal to each other. Okay. When you take the inverse of a vertical parabola, it's a horizontal, and a green one is not a function. Okay. So just because you start with a function doesn't mean when you take the inverse you will get a function. Okay. Basically, when we know here, vertical line test, it is a function. Okay. Horizontal line, it touches twice. So when you take the inverse of horizontal line, you get a vertical line. Okay. So it's kind of like taking that horizontal line and becomes vertical here, and it touches twice. So So then it says the inverse relation is not a function because domain values are paired with more than one range value. For example, the points 9, -3 and 9, 3. Draw the line that passes through those two. What type of line is it? So 9, here, these 2 points, if I draw a line, that's a vertical line, right? So we know it touches twice, it's not a function. When we go backwards from that vertical line, the original would be a horizontal line. So, a couple of definitions here. Vertical line test. So if a vertical line can be drawn so that it intersects the graph of a relation at 2 or more points, then the relation is not a function. So if all vertical lines intersect a function at most 1 point, then the relation is a function. So either one of those sentences, they mean the same thing. Again, we're not going to ask you for the definition of the vertical line test. This definition is not, this test is not the definition of a function. It's how you can figure out whether something is a function. Okay, so the points 9, -3, and 9, 3 are the inverses of -3, 9, 3, 9. Draw the line that passes through those. What type of line is this? So if we go back here, this point and this point, if I draw a line here, what type of line is that? That's a horizontal line. So if you can draw a horizontal line on your original and it touches more than once, in this case twice, then when you look at the inverse, it's not going to be a function. So if a horizontal line can be drawn so that it intersects the graph of a relation more than once, then an inverse is not a function. So in other words, in order for the inverse to be a function, all horizontal lines can only intersect the original and at most one. Okay. So these are just helpful tools. They're not definitions that you have to memorize, but they can help you determine whether something is a function. Okay, so domain and range of y equals x squared. Hopefully you remember. Domain is a polynomial function, so it's all real numbers. The range for that base graph is y greater than or equal to 0. So for the inverse, you interchange them. Or look at your graph. Your graph. The range of the original is the range of the inverse. Sometimes, though, we talked about this in that when we can restrict the domain of the original so that when you take the inverse, you do get a function. So if the domain of the original was restricted in such a way so that its inverse was also a function, what would you restrict it to? So take a look at your graph. Okay. If I, let me erase this. Okay, so if I just took, say, this part of my graph here, okay, just the red, and I took the inverse of just the red, would it be a function? No. Okay, because that horizontal line. If I took that as my red and took the inverse, would it be a function?
Yeah, counting that red.
Okay, so that right there, it would be a function. Okay, so you can restrict it. What about if I so would that be a function? Yes. Okay, so there's more than one possible answer. I always suggest giving me the most that you can. So the most would be this entire arm, or you could do this entire arm. Some of you may be a little bit cheeky and just say x greater than or equal to 9, something like that. Yes, it works. Okay, the most is x greater than or equal to 0, or x less than or equal to 0. Okay, then you would get that arm there, or actually this one, I get the forward. So the right-hand arm, I call it the positive arm, becomes the positive arm on your inverse. Negative arm becomes the negative arm. Okay, but once you include points over that, so that there are two horizontal, then it's not going to be a function. Restricted domain, x greater than or equal to 0. or do you want x less than or equal to 0? Okay, just don't get an overlap there. So here, sorry. No, there's more. So then x less than or equal to 0. You could say x greater than or equal to 1. X less than or equal to negative 1. Okay, so then notation. If we're using function notation, y equals f of x, inverse can be described obviously as x equals f of y, and interchange them, right? If the inverse is also a function, then we can use this inverse function notation. But if it's not a function, then we can't use that, okay? So sometimes we get a little bit lazy and we describe the original. It's a function, we call it y equals f of x. And then we say, instead of saying the words find the inverse, we say find y equals f inverse of x, which is really, can only be used if we take the inverse into the function. So just be aware of that. And that's what this is here. So is this correct language here? Determine f inverse of x given this function. Well, that was the first one that you did. Or, yeah, that was the first one, I think, wasn't it? A line, right? So that, what's the only exception? What line is the only exception to getting a function into the inverse? Horizontal line, right? Because when you take the horizontal line, make the inverse, you get a vertical, which is not a function. So that's the only exception to that. So this, we would get a function. So yes, we can say this, yes, as the inverse is a function. That's the short form of function, Fn. Okay. What we just did was the parabola. Can we use this language? No. Right? Okay, because it's not a function. But if we restrict the domain, okay, we give you some restrictions, then yes, you can use it. So C is okay. Determine f inverse of x. If f of x equals x squared for x greater than or equal to 0, then yes, as the inverse will be a function. Right, because of that. All right, so to summarize here in the chart, in terms of transformation, the inverse of a relation is the graph of the original, reflected over the line y equals x. In variant points, will always lie on the line y equals x. Given the equation of a relation, to find the equation of the inverse, interchange x and y. So mapping notation will be y x. The inverse of y equals f of x, interchange them. And then remember, we like to solve for y. So that's why, WHY, we have that notation.
If you want to like show the reciprocal of f of x, would be f of x 2 minus 1.
Yeah, for brackets.
Yeah.
So that's different from f of x
on each diagonal. That is completely different.
Okay, so if it passes the horizontal line test, so it gets a little bit confusing when you read that horizontal line test. So, in order for the inverse relation to be a function, all horizontal lines can only intersect at most at one point. That's the horizontal line test. So if it passes that, then it's going to be a function. If the inverse is not a function, then you can obtain one by restricting the domain of the original. And then just interchanging these, domain of a relation becomes the range of the inverse. Range of the relation becomes the domain of the inverse. The x-intercept of a relation becomes the y-intercept of its inverse. Y-intercepts of a relation become the x-intercepts. Okay, so then there's some practice. Okay. And as I said, I'm not doing all of them. So on this page, a whole bunch of practice. You'll notice that when you get to E, E is a parabola, so the inverse will not be a function. In F, you've restricted the domain. You've restricted it for me. In F and G, so that means you'll actually get a function, which is the inverse. So then I want to just go to the next page to just to make sure that you don't make any silly mistakes. Okay, so you're going to do a lot of this practice yourself, but we're doing I together and K, and then the right hand side. And then you have some time to work. Okay. So this is a radical function. Domain is x has to be greater than or equal to 0. Okay. So remember back to math 20, approximately what it looks like. So your radical function, then now it's moved down to, think in terms of transformations now. So that's y greater than or equal to -2. Remember, a radical function, it is a function. Okay. Then inverse. So just be careful here. So interchange x and y. And 99% of the time we want you to solve for y. Okay. So get y by itself. What do?
Add 2 both sides, and then, well, you gotta square both sides, but you have to also, when you write the final equation, you have to make sure that you maintain the same description. Right. So it would have to be, what was your description?
So I'm going to square both sides now. So get the y by itself.
Yes.
Square both sides.
And then you need to also state that x has to be greater than the yes, x has to be greater than 0. In this bird, 2 minus 2 in this one.
Okay.
But that, yeah.
So if we do a little sketch of what this looks like, right? So root x minus 2 would be kind of like that. Okay. This would be 4 here. Square root of 4 is 2 minus 2 is 0. This is -2 here. Okay. If we think about what this looks like back from our math 20, -2, 0, and 4 here. If we just graph, if we left it like this, we would have two arms. This only has one. This is our original. So we don't want that arm. So there's not a choice here. The only thing that you can do is give x greater than or equal to -2. It has to be that right-hand arm if this is a positive radical. Okay? So you have to have that. And it makes sense. Even if you didn't graph it or think much about it, this domain has to be your range here. One. This range has to be your domain here. And so that matches with this. Okay? We don't have to show this in bracket notation. We can just comma afterwards. It's kind of like a restriction. If you don't put it in that bracket. Okay? So be careful on that. Oh, and then it says business information. So yes. Okay, now we're going to look at A, the bottom one. So, here, well, we can do our domain. So, remembering back, we're going to spend more time on rational functions and radicals in the next unit, but here we know that x can't be 2. Because you did some stuff on this last year, right? X can't be 2. What about y? What can't y be? Who remembers how to do that? Jackson?
Well, what I do know is that in a rational function, the numerator is that you can use that to calculate the x-intercepts of the rational function. So in this case, y can't be 0. Okay, for the inverse.
Yeah.
Wait, no.
Well, I'm just looking for the range here. What can't y be?
Oh, wait, hold on.
To the original. Remember, if we put in, so this is basically a vertical asymptote, right?
Right.
What about a horizontal asymptote? We talked about it. You go, x is infinity. So let's say x is 1,000,000, which is not close to infinity, but whatever. Big. This would be 3,000,000 over 1,000,000 minus 2. So what y value is that approaching? It's really close to 3,000,000 over 999,998. 3,000,000 over a number that's almost 1,000,000. Right. This too barely does anything to a really big number. So the trick is, the fast thing is that if these are the same degree, take the coefficient. 3 divided by 1 is 3. That can be the horizontal asymptote. Y cannot equal 3. Okay. So, if we do the inverse, and sometimes we ask this on a test, and then the students can't figure out how to solve for y. Okay? This is not really the concept. You need to know how to solve this for y, right? That's using your solving skills back from previous years. So, how do we solve for y? Well, you can multiply both sides by y minus 2. Okay, you need to get y by itself, so I'm going to expand this out. So that's going to be xy minus 2x equals 3y. And again, I need to get y's together. So I'm going to bring this over there. And now what do I do? Draw the y. And so y equals negative 2x over 3 minus x. How else could I write that? So that my denominator has a positive x. Right. Either one of these I would accept. Okay, really it depends on if you brought the 3y over here and the 2x over to the right. You get this right away. Okay? This is actually the nicer form, right? Because the x term is positive here. Okay? So, take a look. What's the domain of this inverse? X cannot be 3. That was our range. Right? What here, how do we find our range of this? What I just mentioned to you before is that if these are the same degree, because anything lower degree after is not going to play much of an effect when you have an infinity that is like billions and billions and billions. Okay? It won't have an effect on it. So here, 2x over x simplifies to 2. So y cannot equal 2. Well, take a look at that. That was our original domain. So it makes sense. So our new domain is x cannot equal 3. And our new range is y cannot equal 2. Okay.
So why can y not equal? But I understand that y cannot equal to y.
Well, if you have a really big number, so if I put in here, there we go. Okay, so that would end up being a 2 here, right? So that number divided by this. So what's that going to be? 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 7. So that divided by this is essentially 2.
Okay. So the limit as
X
x
is
versus infinity is.
Okay, so just on your right-hand side here, we do have to get through these ones on the right here. Some of them are pretty fast. So the point 48 lies on the original graph of f of x. Image point after a reflection. Are we okay?
4.
8, 4. Good. So we've got AB, and we're taking the inverse, that would be GA. Well, the inverse of a linear relation always be a function. I already asked you this. So always, except there's one exception, because Bianca said it was a horizontal line. You take the inverse, it will be vertical. Except So when a relation along with its inverse or graph, there's one invariant point at x equals -4. What are the coordinates? So -4, what would the y value be? If it's invariant. -4, they have to be the same. They have to be on that line y equals x. Okay, algebraically determine the exact value of the coordinates of the invariant points when that is reflected in the line y equals x. So it's like a system of equations, right? Do not find the inverse of this though, and set them equal to 0, right? If this is a problem, I don't even know what it looks like, but let's say, so say it's something like that, okay? And then when you go on its side, so that there, like this, oh, but they're intersecting, so, intersecting. Let's say it's something like this, so then, maybe it looks like something like that, so we have to find these points that are invariant. Those points have to be on the line y equals x. So the easiest way is you're finding the intersection of the original with the line y equals x. So these, that's your system. So remember back to math 20 when we did a system of equations where there are quadratics in it. So we just substitute it, right? So substitute y equals x into y equals 2x squared. Do not take the time to find the inverse of this, because you would have to complete the square to get y by itself. Okay? That will drive me and other teachers nuts. So please don't drive us nuts. Right? You don't want to waste your time. Likely you'd make a mistake along the way. So that's the equation you're going to solve now. And it's a quadratic, so you need to get one side equal to 0. Sometimes it'll be nice and you can factor it, sometimes it won't be. This time you can factor it. Okay? You're not done. Right, Victor, why am I not done? Coordinates, right. Those are x values. That is not a point, okay? And if there are invariant points after an inverse, the coordinates have to be the same. So one point here is going to be, so invariant points will be 1/2, 1/2. You don't have to do any other work, but you have to show them as you are asked to show them as coordinates. Okay? So, common question on tests like that. Okay, question 6. That shouldn't be really an issue. I'm just interchanging those. Okay, so this is domain range of the original. You're finding the inverse. So your new domain is going to, new domain, sorry, instead of the x's, but they're using the values for the original range. And remember, now we have to be a little bit more particular and have X elements instead of nils. And then the new range was the original domain, so A less than or equal to Y less than or equal to B. Get that sorted. Last one, write the equation of the inverse. It might give you a half just for doing that, but as I mentioned, we always want to solve for y, or 99% of the time. So in this case, why is it difficult to express the equation of the inverse in the form y equals? Because we have two terms with y in them, different degrees, right? So how can we express that in a better way for taking the inverse? What's the method that we would do to show it in a different way? Yeah, which is the method to get it there is completing the square. So we want to complete the square on that. So remember back to math 20. Yep.
What do you mean by this? Two terms with y, this degree term.
They're different degree terms, so it's hard to, how do you get y by itself? That's why it's difficult. Right? There's two terms with y, and they don't have the same degree, so I can't get y by itself. So here, remember, back to math 20, coefficient of x squared is 1, that makes it easy. So, I put brackets, I leave the constant out. Half of the coefficient of x is negative 1, squared is positive 1. I add and subtract 1 within the brackets. This is how I do it. Then, I take the minus term out, compensating for any coefficient. There isn't one, so that's minus 1. And then I factor and collect like terms. So that's going to be x minus 1 squared minus 7. Now there's just going to be one term with y in it when I take the inverse. So this is where you solve by the square root principle. You add 7. You take the square root, plus or minus, and add 1.
There's
So
no
you work
d.
backwards. Pardon?
There's no d.
Oh, yours is, sorry, it's labeled a little bit different. So this is C. This is question 7.
So,
No, I don't know. Okay.
No, it's basically, no, it's like R, C.
Close enough.